So we'll repeat what we talked about last time, that we are trying to do a channel, prove the channel coding theorem. So basically we have a channel that is specified by the conditional probability PY given X. And then we have encoder. So, and then you have message, let's say, and then we have decoder that supposingly that decode the message like M hat. So we say it's a lossless kind of transmission of information if the M hat is with high probability that is equal to M. I don't know what's wrong with the touchpad still, but anyway. So and okay, so the way the encoder do is we basically for each M here we will let's see, I may need to calibrate actually. This appears to be bad. See if it works. That's that kind of problem. Let's see if I can. Okay, I will just stay with it. But this is very weird. I didn't touch the screen. You have the dot. So let's see. We have for the M. So for the message, basically after encoder, will generate a sequence of symbols to transmit through the channel. So let's say the length of the symbol is n. Length of the sequence is n. So then, if you think of what's the weight of transmission, will be kind of the amount of information, or you can consider the amount of information is hm per the length of the sequence is n here. And after xn is sent through this channel, then we have yn here, and we'll be trying to recover the message from this yn here. And last time we say we can prove that as long as the weight, so basically the weight then will be basically or the number of messages, if we assume the distribution of the incoming messages is uniform, then the number of messages is will be 2 to the nr. And as long as the weight here is less than the capacity, where the capacity is basically given by the maximum intro information between the input and the output of the channel over the with respect to the input density distribution. And as long as the weight is less than the capacity, then we can show that always we can find a encoding and decoding scheme such that lossless transmission is possible. And basically the scheme will be, we'll just repeat the scheme again. So basically we need to form a codebook, right? The codebook is pretty simple. So a codebook will be basically for each of the message, let's say without loss of generality, we'll say the message will be just from 1 to up to 2 to nr, different labels. And for each of this, the encoding basically for each of this message will map into a sequence to be input into the channel, right? And basically we'll build the codebook as C, I'm using C, right? I think so. So I will have codebook
2 power nr.
C1, yeah, 2 to the power nr, yes.
The maximum of the message, the length maximum, or what?
2 to n hour is the number of messages you can send. Like when you use remember, like each time you have the message coming in, you're using this channel n times basically, because one message coming in, you are mapped into a sequence of length n, right?
Yes,
So a length n sequence. So basically, you use this channel n times and send to the the decoder side. Yes. So I have basically the code book like C1, C2 will be each of these. For example, C1 will be a code word when you have a message, incoming message is 1, and the generation of this code word is simply have a discrete memory source coming from a source like P star X, where the P star X is basically the solution of this guy here. So basically P star X is the argmax Px Ix y. So the idea is like, if you look at again, if you look at the capacity here, it's pretty intuitive, right? It's basically, if currently your distribution into the channel is like Px, then the maximum amount of information can pass through that, like per channel use, will be just like Ixy, the mutual information between the source and channel. So since we want to reach the capacity, we want to pick the incoming distribution is achieving the capacity, the maximum. So then basically, again, the code word here will be just like drawing from this discrete memory left source. So for example, like for message 1, I will just draw a sequence here with length n. So we'll have some maybe x. Yes.
We should find out what is the P star here. We should. That's our goal.
Wait. This in terms of proof is not really your goal. Like when you have actual design, that you may need that, right? When you actually have a channel now, and you want to have design encoder and decoder, you need to find the P star X here. But at this moment, you don't need to, because you know that would be like a maximum for this capacity that will be achieved by this P star X. That distribution will exist. So we just need to ensure that, like, okay, we're going to use this distribution.
So we already know that for this moment, for this case.
Yes, and you can assume you know that. Like how you're going to find it will be a practical problem, but this is like basically just a proof, right? So to prove that, like, prove existence of the encoding decoding pair. So this is just one way to generate to create this encoding decoding pair. There may be other solution, and this is just a way that, okay, this will achieve the capacity. And in practice, it may not be. Yeah, in practice, it's definitely not implementable. But this shows that the existence. And again, we will basically just we'll draw like for message 1, we'll draw a sequence. Let's say just call it whatever, just call C1 anyway. It's basically it's a sequence.
Let's call the book.
The code book is the whole thing. Code book is basically the mapping. So for each of the message, you have the corresponding code word that's your code book. So, and each of these C1, C2 is basically the code word, and the length of the code word will be n. So basically drawing this sequence n times. So I don't know what I use here. Let's see if I have a notation in my slides there. Yeah, let's call it like just use the same notation as my slide. Yeah, but it's okay. I don't actually need to write it down. So let me just use the underscore something. So to indicate, basically I have 2 to n out code word drawing from this source, and each of the sequence here have length n sequences, and this is basically the codebook. And encoding then will be obvious, right? It's trivial, right? So basically encoding will be just going through this codebook. If your for example, if your message is free, you will just send C3 to the channel, right? Through the channel to the channel.
But how to mapping? I mean that how to create the code book?
But that's what I just said, right? You create the codebook. Each of the code is just randomly drawn from this source here. So you just basically draw like 2 to n out sequences from this source, right?
Yeah, that's right.
Yeah, that. Yeah, I'm sure that if I switch back and forth, no, it doesn't do me anything. So anyway, now encoding is trivial, like encoding done, right? Now in terms of decoding, what we are going to do, as we mentioned last time, is we'll just receive a sequence, right, yn, right, from the decoder side. I mean, decoding side we receive a sequence, receiving side we receive a sequence yn, and we'll check whether we can find a code word, let's say CM hat, that is jointly typical with this like yn. So if such, let's see, M hat exists, and also unique output M hat. So basically what we are going to do is we are going to, interestingly, if I touch one of the screen, then I don't have this problem anymore. Maybe I will just do that. So if such M hat exists, then we will just like output like M hat, and also like we hope that like M hat is unique. So if M hat is not unique, then we'll just otherwise we'll declare error or declare failure. So it's very simple, right? So, and then of course the question is like, what's the failure rate? That is, we hope that the failure rate is sufficiently small, then we can claim that there will be like lossless transmission. Yeah.
And why M hat should be unique?
Well, that's what I'm saying. Like, it doesn't have to be. If M hat is unique, then you will consider M hat is your output of the decoder. If it's not unique, you declare failure.
I mean that why it should be unique?
Okay, as I said, like if it is not unique, you declare failure. We still need to analyze that. It's not done. It's just like how you're going to do the decoding. We need to analyze. Like, okay, the next question is of course like, what's the probability of failure? Right. So we want to make sure that this is kind of small, sufficiently small, then like we are done, right? So I guess we ended just trying to look at like different error events and only talk about one error event. So are there multiple error events? Let's maybe put them down first. So first one, I can have the error event is basically, maybe I write error event. So this is like, or like you can say failure event. So failure happen if like CM and YN are not jointly typical, right? So because we want to decode back like M here, if it turns out like this is actually not jointly typical, then it will be an error, right? So then let's see another error event. Exists. Okay. Error event 2. So exists M pi, let's say, not equal to M such that CM pi YN is jointly typical. So in that case, even though we don't fail in the first case, so let's say like CM is actually jointly typical with YN, but like if we have another one is also jointly typical with YN, then that would be not unique, right? As you just kind of like ask like why it should be unique. It doesn't need to be unique actually. So but in that case it will be a failure, right? So we just need to study like what's the probability of failure here. Yeah. So and then like the probability of error, or like I should say the average probability of error. I want to be clear here. Why is average? Because like the coding argument, the code, you can think of like we have this whole generation of this code is randomly generated, right? So therefore, like each time you generate a different code, the error probability can be different, right? So because each time we basically generate different code, both each time will be like a different error probability. But the average error probability will be bounded by the error events, these two error events, right?
What's that?
Or the probability of like event 1 and probability of event 2 here. So, I mean, like in general, like you can say like union of like E1 plus E2, like or like this should be probability.
What is the notation, Professor? What is it?
They exist.
Exists. Oh.
Yeah, that's math notation. They exist. M pi is not equal to M such that like Cn pi Yn is jointly typical. So and then the error is like average probability error is just probability of the error event 1 union error event 2, and there's a union bound here. You can like bound it by like PE1 plus PE2, something like that. Okay. Yeah. Then we look at each of the error event. I guess like last time is we argue like by the end we say like this will be close to 0. This will close to 0. Yes, this will be close to 0 because the argument is like you have like Cm is basically coming from a source P star Xn, right? And then like this one will go through a Py given X, the channel conditional Py given X. And then if you look at them together, this is actually like going through a joint distribution like Pxy, right? So anything coming from a joint distribution Pxy for sequence Xn and Yn, and as long as Xn and Yn is sufficiently large, then they will be jointly typical, right? So therefore, like this is a probability not to be jointly typical that will goes to 0. Yes. And then like so then we look at the second one. So let's say if like we have some M pi, it's not equal to M, but then like M pi and Yn is jointly typical. Now if I have some other M pi, there's also I can, maybe I'll use the same thing here.
So there is some m at n5. There's no m.
So some other m pi
Yeah.
that's not equal to m. Now, because it's not equal to m, it won't go through the channel, right? So because it's not related to, it's not, we send cm through the channel, but we didn't send cm pi to the channel, right? So therefore, it won't go through this channel, right? So basically, like you will have this cm pi and yn should be independent.
Yeah.
So then we have earlier we talked about like packing lemma, right? We say if like we have two independent sources, what's the probability this two independent sources will be jointly typical, or like how many of them can be packed? I mean, given some yn, and I want to see like how many xn can be put into that is independent to yn, such that like this none of this xn will be like jointly typical with yn, right? We studied that, like, and the probability is basically is bounded by, so therefore like probability of E2 is bounded by like 2 to the n I xy minus r minus 3 epsilon, right? Okay, you can go back and check. This is basically the packing lemma.
That's the probability of that E2.
Yes, that's the probability of E2. So therefore, like then you see, like because we argue that R is less than IXY, right? Or like R is less than wait, I should be careful here. Wait a sec. So what is IXY here? IXY here is actually equal to the capacity, right?
Yes.
Because I pick Px to have the same distribution of P star x. So therefore, like IXY should be equal to capacity.
Yeah. So
this is saying that as long as the capacity, weight is less than the capacity, then this, yeah. And of course I have 3 epsilon here, but I can make epsilon arbitrarily small. But as long as weight is less than capacity 3 epsilon, or this can be make arbitrarily small to 0, so this can close to 0, then this probability, yeah,
yes, that's right.
this probability will goes to 0, right?
Goes to 0.
Yeah, because this is
And it's
n is high, and we can make it arbitrarily high. So assume n goes to infinity. So, and then therefore, like the overall average probability will
0.
go to 0, something like that. Yes, that's basically the main idea of the Ford theorem. There's some remark here though, like a little bit caveat. As I mentioned, this is actually the average error probability because we each time think of like you pull out a different code book, will have a different error probability, right? And then like if we want to say, okay, how about we want to say more concrete, like can we say like what's the, because at the beginning of the theorem we are saying that like we can find a code book such that the error probability go to 0, but here the conclusion is a little bit different. It's saying that like if we use a scheme here to generate many code books, generate many coding scheme, then the average error will go to 0.
Yeah.
So this is a little bit different from the original statement.
So we always get the we always get the original message. There's no error in there. If like that, there's no possibility to get error if we have to kind of that condition. We never get.
No. Let me repeat again. Like the two different statements is the following. The original statement is saying that like we can find a coding scheme such that the errors can goes to 0,
Yes.
right? But now, like what we show here is that we actually have a random codebook argument that we can generate a number of codebooks, like a random number of codebooks, and on average, among all these codebook, all these coding schemes, the errors will go to zero. The average error will go to zero.
Yeah.
So that's a little bit different from the original statement. But so, or maybe I can write this way, like the original statement is like we want the probability of error given some codebook, and for the message m, let's say it will go to zero, right?
That's right.
And but what we show, or like let me just even I can.
Now we have any code book that will be going to zero also.
Let's see. Wait, it's a little bit different. Let me see. I think maybe I have something wrong with my slide, but let's see like if I can fix it now. Yeah, that's what we want here. That's what we want here. It's like for any, we can find some codebook, and for all messages, we want the error goes to zero. And what we show is basically given yeah, in my side I wrote this actually. I wrote that, but I'm not.
There is no and.
There
is no and there.
Yes, there's no M there, but I'm thinking like may not be right, right? Did we show this? I think we more or less showed this instead. So for any message, we um, okay, but I think yeah, it's okay. We can use the same argument. So yeah, that would be problem. Like let's see, can I actually can I from this convert to that? Like let's see, for it seems that I said like I fix a message.
If you're not satisfied the C star, it cannot be converted to that.
Let's say that again.
If the M is not satisfying the C star, so it's not cannot be converted because the will be the map will not be will maybe will more than maximum of channel capacity. Meanwhile, C star is a limit to the channel capacity.
Oh wait, this is not the capacity. This is a code book.
The code book that
That's a different code book. Like
capacity.
it's not. So it's saying that okay, I have like different code book here.
Different code book.
So I want to say that like eventually I can able to find a code book C star, and also like for any message M, the error is going to go to infinity.
Oh,
Sorry, going to 0.
so it means that for any code book that
No, not any code book. For some optimum code book. So let's say we find some optimum code book, and for any message, but like any message, for any message, for any message M, that exists a code book C star such that this goes to 0. That's the original statement, right?
Yes.
In the notes, I said I showed this. I said I showed this, but I'm thinking that more or less we showed this instead. Let's see. So
It makes sense. It will be error will be going to 0. No need the code book in there.
given the let's see, if can we start from here? Let's say for error some message M, my errors. Okay, anyway, I guess I should just come back here. It's just a remark. So maybe I'll come back, I'll think a little bit more, and then like maybe come back next time for this one. But this is actually a rather interesting argument that I'll show instead talk about this. I'll just maybe I will give you a homework exercise for that, like using a similar argument. But the argument would be more or less like if you have the average of something, some random variable, then you can give a bound to all of the elements. For example, like actually that's basically. By the way, I think that is probably a Markov inequality that we talked about last time, some times ago. But maybe I give another example is related. For example, like if I have a bunch of students with some height like equal to the average height is 170 cm, and then we can, okay, this is maybe a little bit silly kind of like argument. We'll say like the upper half of the student, that's the taller half of the student. This would be extremely silly if I put it this way, but the taller half of the students cannot have average height larger than a 340 cm. So it's extremely silly when I put it this way, but you agree with that, right?
Yeah, that's right.
Yes, and that's basically from the argument that like if I sorted all the students with height from tallest and shortest, then if I have an average, it's like somewhere like in the middle, average height is like
170.
Yeah, 170, let's say. So then that means the mean here. If I look at the taller half here, if the taller half have height is more than like double of this average here, then simply look at the contribution from the upper half to the entire average will be more than like 170, even if like all the rest basically have low height, like if all the height is equal to 0. And that give in general an argument is like something like if you
It should be upper half taller maybe.
upper half,
Upper half taller.
yeah, upper half taller, yeah, upper half of the taller student maybe like the tallest or taller, I don't know, cannot have like average height more than that. Or actually, this does not need to be average height exactly equal to that, right? Average height, I can say average height is if average height is less than 170. If I say average height is less than 170, then the upper taller half cannot be larger than like 340. So for the L probability we like to talk about earlier, we'll have some arguments that I need to kind of like short out completely, but it'll be something like we know the error, average error, if it's equal to, let's say, some E here, and we know the E is going to be 0. And the average, let's say this average error is due to the fact that we are going to use a, oh actually maybe I think of that, it probably is okay. So the average over, yeah, may not be okay, but anyway, so let's say it's E and it's go to 0. Now this average is coming from like I have oh, actually, it's okay. Actually, I can sort out the argument. So let's say I have like n different code books here, right? That's, or like I don't use n anymore. Maybe like a big m different code books. All these code books I eventually have the average error probabilities is equal to E going to 0. Now what I can do is I can no, actually I cannot. Actually, this argument does not work. But if I have instead like average error over like all the messages, it's going to be E. Then like what I can do is say I can eliminate some of the bad messages. So for example, like let's say I have 1, 2, and so on to the NR. Some of the messages have like high error probability, some have lower error probability. So what I can do is say I will eliminate half of the messages. Eliminate in the sense that like I'm not going to use those
message.
Yes. So in the sense that I can only send half as fast as before, because now I don't have these labels. So my call rate will reduce from what? From 2 to the NR to 2 to the N, or like number of labels will reduce to 2 to the N to 2 to NR over 2, right?
Yes.
But 2 to the NR over 2 is just simply equal to 2 to the NR, something like that, right?
Yes.
But then like, as n goes to infinity, again the weight will be decreased very small, because r minus n minus 1, right?
Oh, okay, that's right.
Right?
So
Because this is equal to 2 to the n r minus 1, right?
yes.
I just put out n here, so I have n r minus n 1 over n here.
So it means that will be 0 n minus n.
Yeah, 1 over n will be essentially go to 0.
So
So the weight only decreased like kind of like by 1 over n. But however, now I can claim that like for all the messages. Oh, okay. Wait a sec. Actually, for all the messages. Oh, actually, oh shoot. I need to even correct my original statement here. My statement is a little bit wrong here. Of course, I will have FHI is bigger than 40, but I can even claim that like this is like basically, I can go even stronger. It's the minimum height among the upper half. Yeah, or like the taller half is at least 340. Right. I mean the average is 340 there. You look at the lowest one, of course it's always at least 340, right? Wait a sec.
That 340 is the highest.
Oh, okay. I need to go back. It cannot be. Well, yeah. We say we cannot have, right? We cannot have bigger than that. So that means I have to be smaller. Have the average have to be less than that.
Yeah,
have to be.
Yes, that's right.
With the F. Oh, okay. Make it pretty messy. The average height of the have to be less than 330.
Yeah.
So
that statement.
If the average is less than 330, the minimum cannot be like more than 330, right? Because the minimum is already 330. The next one will be larger than 330, right? And the next one will be larger than 330, and so on. Then of course the average will be more than 330.
But the maximum is 340. But why more than that? We have.
Oh, sorry. At most. Yeah. I'm sorry. Yeah, it's
at most.
Yeah, at most 330.
Oh, so the maximum is still 340.
The mass. The
The maximum.
No, the maximum is not 330. The average cannot be more than 330, right?
Yeah.
Cannot be more than 330. Because as we said here, like if an average already more than 330, only look at the average of the second half, it will contribute more than the average of 170, right? Even I ignore this half here.
Oh yes, that's right.
And then consequently, like I cannot have the minimum have like more than 340, right? Because if this guy here already more than 340, if all the shortest one among the taller half,
I think
yeah,
that can be less than 340 from the first one in here, because a 340 may be in here for this one only. So 340 may be in here. So this is maybe will be less than 340. So yeah. That's right.
You can't wait. Let's see. Wait. That's the point. It can be less than, but it cannot be. Cannot be more than, right? Therefore, like it's at most. Like I made a mistake at the beginning, but it's at most, right?
Yeah.
It's at most. It cannot be more than 340.
Yeah.
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 Yeah. So if it's more than 340, then the rest of the fellows will be like more than 340 as well. Then the average must be more than 340, right?
Yeah.
So that means that
Yeah. So when that average is really 340 at the half.
yeah, and
That's probably will be more than 340.
oh, actually, yeah, and we can use the similar argument, but the other way around. Actually, I made a bad argument here, but you can show that like in the other way around that like, so I can also have this L probability here. If I use the better half here, the better half here.
It's less than.
Now in this case, the opposite.
Yeah, the opposite.
The better half here. The one with smaller probability, the better half will be the one with smaller error, right? Smaller probability of error. The minimum one cannot have. Let's say I just use this better half. The error probability let's see, the maximum error probability cannot be more than (2e). Let's see, it makes sense.
Cannot be more than 2.
Yes, actually, that makes sense because if the maximum error probability here on this lower half is more than 2e, we have a kind of similar argument. Then, like on the other side here, this one will be more than 2e, right? The next one in the upper half here. So, let's say.
But if there is outlier data, so that can be more than 2.
No, it won't because you look at this again. So I have like error probability, then I have average like this. Let's say the average is here is equal to e here.
Yeah, equal to e there.
Now I have two half here, right?
That's right.
I have two half here. Now let's say the average is equal to this one is the average.
Yes.
And now let's say this one here, if it's more than like this average, 2 times this average.
That's one. That's in there.
Yeah, because we say the lower half. In this case, we look at the lower half. If the maximum among the lower half is more than 2e, then the rest of these guys will be more than 2e as well, right?
Yes.
So, and that's basically what just say at the beginning. So if like the upper half here is more than like 2 times the average, then just counting this side alone will have a contribution more than the average, right? So therefore, like it will force like on this other side to have
More than 2.
actually this is I can even write down this consequence also, right? The minimum height of the taller minimum height among the taller half is at most 340. That's actually consequently is the maximum height of the shorter half is actually I'm not sure this consequence is this side. Let's see, is at most 340. Yeah, actually this consequence is right? Because if you can't, we are saying like this guy cannot be more than like 2 times E, right?
So that's in.
And this guy is taller, is more than this one, right?
Yes.
Yeah.
So in here, maybe can
Yes.
you start off?
Yes.
In here that will be precise 2E, and for the second and the first one in here will be precise 2E in here.
No, actually it's not precisely 2E. It's more like it cannot be more than 2E.
Cannot be more than 2E.
Yeah, if it's more than 2E, then the entire average will be more than E, right?
More than 2E will be more than E.
Because if this guy is more than 2E,
Yes.
this guy will be more than 2E, right?
That's right.
And then all the rest will be more than 2E.
That's right.
So only the kind of upper half here, you have like the contribution to the average is more than E already, right?
Okay.
So then like even I don't count this side, so there's no way the average is equal to E. Yeah.
Yeah, that's right.
So that's why like from this one here, what we can do is like assume that I need to double check, but if we assume that like we have a code book that the message actually I it's kind of bad. I think I have everything now. I have all the argument now. So but let me finish this one. So if the average over all the messages is equal to E and E equal to 0, or like average message over all messages is equal to E, then we can argue that like if we discard the worst upper half with more error probability, just remaining the better lower half. The worst case for the better lower half, basically the one with the maximum error probability, cannot more than 2E, right?
Cannot more than 2E.
Yeah.
Why?
Oh, okay, it's back to here, right? So if the average here is equal to E, let's say, right?
Yes.
Average of everyone is like, let me draw much better. Like I'm sorry, like my drawing is too bad. So let's just look at 6 bar here, something like that, right?
1,
6 bar. I sort the error probability here.
2, 3.
So I have one half here, lower half, and like
Yes.
a worst half here, better half. Well, I argue like if the average here is equal to E, so let's say this is the average.
The average is not there.
Yeah, the average is not there. It shouldn't be there.
More.
Well, I would say like why the average would not be here, right? So let's say the average is somewhere here. So
But the logically should be here.
yes. Yes, I know. But I that's why I want to argue that like this E is incorrect. This is not the right E here.
Okay.
Because let's say if I have this is like the average, and then I look at the lower half. If the lower half like this value is bigger than 2E,
Yeah,
then the next one has to be bigger than 2E as well, right?
that's right.
Then the next one has to be bigger than 2E as well.
Yes.
So just look at the contribution for the upper half. The average should be more than E, right?
Yes.
Even I ignore this 0 here.
Yeah.
Let's say, so that's why like look at this lower half here. Basically like given I have like given average error equal to E, let's say, we can conclude that the lower, or like I say, I can write lower, or like I just better half have error probability no more than 2E, or like less than 2E.
Oh yeah, that's right.
for all of them.
Yeah.
Yeah. So then like this will basically complete the argument. So now let me go back to sort things out. I guess let me go back to sorting out. This is bad. I'm sorry about that. So it makes a little bit confusing. Go back like what the original statement said. It's like we have the probability of error. We want to say that exists for every message, right? Exists a code, let's say called C star, such that this C star and this message will goes to 0, something like that. That's the original statement. Now what we prove is basically that for the average error, probability error go to 0. And let's say this is average over all code book and messages. So even though we start with like picking a message M hat, but anyway, like this is true, right? Because it just say that like for any particular message, the average is actually, or maybe I write like that. We did that, right? Probability of error given the message goes to 0, right?
Yeah.
But that immediately implies this, right? Because this is just an average of this guy, right? Average over, we're basically saying like for all M here, this go to 0. Now then, of course, like if I also average over all the messages, it also goes to 0, right? So then like from here, since these ones go to 0, there must be one code book is good, right? Because this average, like P error, can be equal to some E again. But then if there's some E here, at least there's one is better than E, right? Will be like smaller than E, right? So therefore, like I will have like P error for some code book will be less than E, right? That's obvious, right? Or less than equal to E. Yeah. It makes sense, right? So and this will go to 0. Oh, now I cannot write. Let's see. Huh. Let me finish this and then
for some code that
for
for
some
code that will be less than E, but for some other code that will be more than E.
No, yeah, it's fine. But I just look for one particular C star, right?
Yeah.
I look for one particular C star, and that C star it works is fine.
Yeah.
So now then, now this is very difficult now because I cannot write. But I will just finish that. So then like this goes to 0. Then we can go back to argument earlier on. Now this go back to the one we just say. Then here we can argue this one will. Where's my cursor here? Yeah. We can argue that going back to this one here, right?
Yeah, that's right.
By the argument we just have earlier. So what we have is like, now we're trying to, for this particular code book, we have the average error goes to 0 is equal to E, let's say, cannot be bigger than E. Now I can discard like the worst half there and just like keep the better half. And for the better half here, we'll ensure that the probability of error is at most 2 times of this E. So therefore it's still going to be 0 for each of the messages.
2 times.
Yeah.
Yeah. That can be 2E.
Yeah, that will be like bounded by 2E. Yeah. This is extremely difficult, honestly.
2E.
Yeah, without the stylus, I need to, I don't know what's going on.
Stylus?
Yeah, suddenly it dies. It's very weird. So it's like less than equal to 2E, right? So therefore it's still going to, that's basically we get back the original statement that we want to show. It's like for any messages, and we know that even though we discard half of the messages, the rate only decreased by 1 over n, right? So still the rate can be arbitrarily close to the capacity as long as n goes to infinity. And that's basically the entire proof. So sorry about that, it was a little bit pumpy. So
So what is the E then?
the E here.
And the value of E. How could
That basically would be like this one. No, we don't actually here is a we don't need one or need or one to calculate that. It's from this one, right? That's the average probability of error expanded by this guy, right? Let's see if I can use a cursor instead, since I.
So E is epsilon in there. The same is similar to.
E is here, right? So it's bounded by basically that probability error. There's one error we claim that is because of like, if you have joint source, it's always jointly typical, right? And then if using the packet lemma, as long as you are less than the capacity, it also goes to 0. Right? And then like, as long as this sum is going to 0, we don't actually care what's the exact value E there. We just want to.
So E actually that's the probability of E1 and.
Probably E1 plus E2, yes. And
Less than
yes. So we don't care like what is it exactly, but we just care that it goes to 0.
Yes,
Yeah.
0.
As n goes to infinity. So because of that, then we can claim that like there's such a scheme exists, right? Like we can find a code book that actually can have the probability of failure given this coding scheme. The probability of failure goes to 0. Therefore, this will be a lossless transmission, and the weight can be arbitrarily close to the capacity. Yes, that will be the forward theorem. So I guess like I will stop here for like a break for 15 minutes, then we'll come back like so I need to fix this first. I don't know why my stylus stopped working. That's very annoying. Let's see.